Hello and welcome. In the previous video, we looked at the network core. We looked at the difference between packet switching and circuit switching. We also discussed the current internet infrastructure. Now we are going to discuss some of the performance issues related to the networks, in which we are going to discuss delay, loss, and throughput. We'll also discuss a little bit about the security in the networks. So the question is that why do packets get delayed and why does loss occur into the networks? In this picture, you can see that there are two hosts A and B, which are transmitting packets towards the router, and you can see on the router that there is a queue of packets that gets created. Now, the reason that these queues get created on the routers is because if the arrival rate at the input link is going to exceed the output link rate, then we will have queues created on the routers. Now remember that the routers have a finite buffer size, which means that if it keeps going like this, that the arrival rate is always higher than the uh, uh, higher than the rate at which the packets are being transmitted on the output link, then eventually this buffer is going to get full. Once the buffer gets full, then the packets will be lost. The router will start dropping the packets. How these packets are dropped, which packets are dropped, we'll leave this for layer 3 discussion. So here you can see that the packet here, which is going to be transmitted, we consider this as the transmission delay, the time it takes, and we talked about it in the previous videos, that the transmission delay is L by R. L is the number of bits in the packet, and then R is the transmission capacity of the link. The queuing delay is the time that the packet will stay in the queue waiting for its turn to be transmitted. There are basically four types of delays in total. There's there's a processing delay, we call it dproc. There's a queuing delay, dq. There is a transmission delay, and then we have the propagation delay. Let's have a look at how these delays are different from each other. The first one is the processing delay, which basically you can also call it nodal processing delay. It basically means the delay or the time that it takes for the router to process this packet. By processing, what we mean is that the router is going to check any bit errors in the packet, and it is also going to determine to which output link this router needs to forward this packet to. And it will consult the routing table for that. So all this processing of the packet to check the bit errors and decide on the output link is basically the processing delay. And this delay is usually or typically in microseconds. The second delay is the queuing delay, as I mentioned in previously, that the queuing delay is basically the delay that the packet is going to face while staying in the queue, waiting for its turn. Now, the queuing delay, it's usually variable. So it also depends on the congestion level of the router. Also, how much congestion is there on the network. So it really is difficult to measure what exactly is the queuing delay because it may be variable. At sometimes there are no queues. If there is no congestion on the network, then we will have no queuing delay. But if there's more congestion, then this delay can increase. The third type of the delay is called the transmission delay. We talked about it earlier. Transmission delay is basically L by R. L is the bits, the packet length, and R is the transmission rate. Finally, the propagation delay is basically the delay or the time that it will take for the packet to be sent from one node to another node. Now, it depends on the distance, how far they are from each other, and it also depends at which speed the packet is going to be transmitted. Now, remember that there is a difference between transmission delay and propagation delay. They're completely different from each other. Transmission delay basically means that how long will it take to transmit this whole packet into the transmission link, not that when is it going to reach the other node. So the amount of time, again, I will repeat, the amount of time that it will take to transmit this packet onto this link is the transmission delay, and that is L by R. Propagation delay is the time it will take for this packet to go from one node once it's transmitted on the link to the other node. That is the propagation delay. So this is D by S. Now the propagation speed, it really varies from depending upon the transmission medium, but it's usually 2 cross 10 raised by 8 meter per second, a little less than the speed of the light. Let's have a look at the caravan analogy to understand this, that how much time it will take for these bits to be transmitted from one router to another. So in this particular example, we are taking the caravan analogy. So here, each car is representing a bit, and the whole caravan is basically representing a packet. The toll booth is representing the router, and the toll booth will take 12 seconds to service the car. So in other words, we call this as the bit transmission time. And the distance between two routers, or in this example, the distance between the two toll booths is 100 kilometer, and the cars will propagate at a speed of 100 kilometer per hour, right? So how long until this caravan, the whole caravan of 10 cars, is lined up before the second toll booth? So first of all, we have to calculate how long does it take for this toll booth to process or service all these cars. And since it is 12 seconds to service one car, it basically means that this toll booth requires 120 seconds to process or to service all these cars. After that, the time that it will take for the last car to reach is basically 100 kilometer divided by the distance divided by the speed, which is again 100 kilometer per hour. You basically means that the car will take 1 hour to go from this toll booth to the second toll booth. So in other words, 1 hour plus 120 seconds is the total time, which is 62 minutes before these cars are actually lined up in front of the second toll booth. We will also look at some of the similar examples. I will create a separate video on some of the problems related to chapter number 1. So stay tuned. Now, suppose that the cars now propagate at 1,000 kilometer per hour, and suppose that the toll booth now takes 1 minute to service a car. Will the cars arrive to the second toll booth before all cars are serviced at the first booth? Now, I leave it up to you to calculate this. Let's have a look at the packet queuing delay a little bit in more detail. Now, one of the parameter that we did not consider is the average packet arrival rate. In the previous example, when we were discussing these delays, we were considering that the packets are arriving at a constant bit rate. However, the arrival of these packets might vary at different times. So we need to consider the average. So we will take another parameter A, which represents the average packet arrival rate. L is the length of the packet in bits, and R is the transmission rate. So in other words, now the expression looks like this. L into A, which is the arrival rate of the bits, the average arrival rate of the bits, and then divide by the rate at which the bits are going to be transmitted. R, we call this as the traffic intensity. So if the traffic intensity, which is L cross A by R, is approximately equal to 0, it basically means that we will not have a queuing delay, or it is going to be very, very small. But as the traffic intensity goes on increasing, in other words, if the average arrival rate of the bits keeps on increasing, then it basically means that the delay will be larger. So if L into A by R is greater than 1, or it is approaching 1, the queuing delay will be larger. But if it exceeds 1, it basically means that there is more and more packets are arriving, but they're not being serviced at the same rate. It basically will lead us to this situation where we will have an uh, infinite delay. So this is just to show you an example. If L into A by R is approximately equal to 0, you basically have the highway is completely free and there is very less traffic. But if the arrival rate keeps on increasing, you will have basically a queue that will grow bigger and bigger, and eventually it will reach infinity. Let's talk about the real internet delays and routes. And how do the real internet delays look like? So there is a program called traceroute that can be used to measure the delay in real time. What traceroute does is that it sends 3 probe messages to the first node. These 3 probe messages are ICMP packets, and then it calculates the time. How long did it take for these probe messages to go and then come back? Then it does same with the next hop in the route. Then it does the same with the third hop in the route. And then basically this goes on and on. So this is how the output looks like if you run a trace route on gaia.cs.umass.edu from this host to this host. So you can see here that the first hop or the first router to which these packets were transmitted, the delay is 1 millisecond, 1 millisecond, and 2 millisecond. And as we go, that the number of routers and physically the distance becomes bigger and bigger between the source and destination, you can see that the delays are increasing. So from 1 millisecond to 6 millisecond, 16 millisecond, 21 millisecond, 22 millisecond, and it keeps on increasing. Especially here, you can see the transocean link. It is 22 to 106 millisecond. The delay has increased. And sometimes these delays might reduce as well, but overall, what you see here is that from 1 millisecond, the delay went up to 26 millisecond and 128 millisecond. And then eventually it's 132 millisecond before it reaches the destination. If in your output, if you see static, it basically means that there is no response coming from that router. Either the probe is lost or the router is configured not to reply back to this. Let me show you this in real time as well. So you can do it on Linux or on the Windows. In Linux, you basically have a program called traceroute, and here I'm going to use trace. So the command is tracecert, and I'm going to send request to kta.se, which is in Sweden. So I wanted to see how the delay, because if I send this local request to some some web server which is in the same city, we might not be able to see the significant delays. But because this is hosted in another country in Europe, so let's see how we see this delay increasing. So you can see here, the first request usually goes to the gateway, and the delay is 2 millisecond, 1 millisecond, and 1 millisecond. And then it goes to the second hop. It is 45 millisecond, which is quite kind of surprising. Shouldn't be that much, but here you can see that the fourth router or the fourth hop basically did not reply back at all. And then some of the probes are lost, but let's see what is the final output. And you see here that it has reached 9 hops and the delay is 55 milliseconds so far. Like I said, sometimes the delay might be reduced. There could be plenty of reasons for that. But now we see that it basically started going into the European region, crossing the oceans. the delay is increasing and increasing. So it started from 1 millisecond to my gateway, and it has reached 172 millisecond. So the physical distance actually matters a lot, along with the other factors, of course. So now you can see that it is in Stockholm, and then eventually, after going through 27 hops or 27 routers, you can say, it finally reached the destination, which is www.kth.sc, and the delay is approximately 150. We can take the average 150 millisecond. So that is the real time delay that you can see. All those delays that we have been discussing, the four types of delays, the processing delay, the queuing delay, um, the transmission delay, and then the propagation delay. And propagation delay, we talked about it, that it really depends on the distance as well. So all the delays are coming into play, and then we get this total delay of 172 milliseconds to the final destination. So you can also try this for any server, and you should be able to see the delays. So we talked about the packet loss earlier, that the queues, they basically get created on the routers, buffers, and because the router buffer has a finite capacity, if it gets full, then the router is going to drop this packet based on certain factors. Let's talk about the Let's now talk about the throughput. So what is throughput? Throughput is basically the rate at which the bits are transmitted or sent from one end to another end. So from this server to this client, the average rate at which the bits are transmitted is called the throughput. So there are two types of throughput. One is called instantaneous throughput, which is basically the rate that you measure at a given point in time. Whereas the average throughput is the rate over a longer period of time, or in other words, the average rate is between the sender and the receiver. Now, if we consider this as a pipe which can carry a fluid at RS bits per second, and if we consider this pipe which can carry the fluid at RC bits per second, so this one appears to be a smaller pipe and this one appears to be a bigger pipe. Now we have to measure the average throughput between this source and this destination. So remember that the average throughput is always the lowest or the bottleneck between two hosts. So in this case, for example, RS is less than RC, so the average throughput is going to be RS bits per second. Whereas in this scenario, if RS is bigger than RC, here RC is the bottleneck, so RC bits per second is going to be the average end-to-end throughput. So it is always the bottleneck that basically defines the end-to-end throughput. Let's have a look at this throughput scenario in which we have, let's just say that we have these servers. These are 10 servers. These are 10 clients. The throughput between server and the backbone is RS bits per second. Here, the backbone has a throughput or transmission rate of R bits per second. And on the client side, we have RC bits per second. We also assume in this scenario, for the sake of simplicity, that this backbone is fairly shared between all these 10 connections. What it means is that every connection between a client and server is utilizing R by 10 bandwidth. So what is the average throughput in this scenario? So we have three kinds of transmission rates. We have RS bits per second, we have RC bits per second, and we have R by 10 bits per second. So in this particular case, whichever is the minimum among these three, that is going to be the end-to-end throughput. What I mean is that if RS is is, for example, 5 megabits per second, this is 10 megabits per second, and this is 12 megabits per second, then RS is the bottleneck, so the end-to-end throughput is 5 megabits per second. However, if the bottleneck is here, if R by 10 is, let's just say, 2 megabits per second, then the bottleneck is on the backbone, which is rarely the case, but just to take an example, then the bottleneck is here. It means that the end-to-end throughput will be 2 megabits per second. So whichever is the lowest, that is going to dictate the end-to-end throughput. So with this, we have discussed what are the performance issues on the network, what are the different types of delays. Now let's talk a little bit about the security. Now you have to understand that internet was originally designed with no security in mind. So when you have no security in mind, it basically means that all the protocols that we designed, they basically are insecure protocols. So if I take an example of an HTTP protocol, which is used for web access, it's basically an insecure protocol. There's no security in it, and that is why it is vulnerable. If I talk about FTP, file transfer protocol, again, no security. SMTP protocol, simple mail transfer protocol, no security in it. DNS protocol, domain name servers, which is one of the most critical protocols on the internet, there is no security. So originally, the internet was designed and the protocols were designed with no security in mind. And now we are playing the catch up, which means that if you want to secure HTTP, you have to use HTTPS, which is a secure socket layer. If you want to secure your FTP, you have to use SFTP or FTPS, SSL on top of the FTP protocol, and so on is the case with all the protocols. In terms of security, we have to think about implementing security on all the layers, starting from the application, transport, network, data link. If we really want to have security, we need to apply security on each of these layers. We also call this as defense in depth. We also need to know how the attackers or the bad guys think. Because if you want to protect your network against the attacks, you need to think like an attacker. You have to find the vulnerabilities in your network, and then you will be able to design and secure your network. Some of the types of attacks that are possible on the networks, one of them is called sniffing. So what does it mean by sniffing? Sniffing basically means that an attacker is sitting on the network and he's actually capturing and recording all your packets. Now, when we had hubs in the network, sniffing was pretty easy. Why? Because hubs, they broadcast the packets into the network. And anybody connected to the network, if he turns his NIC into promiscuous mode, he can listen to all the traffic and capture. So if there are username and passwords traveling over the network in the clear text, he can easily capture those username and passwords. But with the introduction of the switches, which are more intelligent than hubs, sniffing is now a little bit more difficult. I wouldn't say impossible because we can still launch attacks like ARP poisoning, for example, to sniff the packets, but we no longer can do passive sniffing in these networks. So in a switched network, you have to do active sniffing or you have to launch an active attack like ARP poisoning to redirect the traffic towards the attacker's machine. Any tools like Wireshark, EtherCap, BetterCap, they can be used, ARP spoof, they can be used to capture the packets on the network. The attackers can also fake the identity. We call this as spoofing. They can spoof the IP addresses and pretend to be somebody else. They can inject packets into the network with the false source MAC address. They can also do MAC spoofing. So spoofing is all about changing your identity and pretending to be somebody else. There could be different reasons for IP spoofing or MAC spoofing or faking the identity in general. It probably could be to bypass some security filters, or it could also be used so that um, uh, the attack cannot be traced back to the attacker. We also have denial of service attack in the networks, which basically means that the attackers they try to try to launch multiple or send bogus traffic towards the server and try to bring it down. There are many different types of denial of service attacks. Well, denial of service has largely been replaced with distributed denial of service attacks, where basically lots of machines or bots they attack the single host or the single server. In this example, you can see a kind of distributed denial of service attack where the attacker takes control of the bots or computers on the network and then uses them to launch an attack on the server. Now, remember that distributed denial of service attacks are pretty difficult to handle or to prevent without the support of the ISP. Some of the DOS attacks that are on top of my head are, for example, there is a slow loris attack, there is a Smurf attack, a ping of death attack, ICMP flooding, um, TCP SYN flooding. These are some of the examples of denial of service attacks. So what is your line of defense? How can we prevent or provide security? Well, this is just some of the uh, defensive mechanisms that are listed here. So one is that you can use authentication on your network, whether it's you know user and password based authentication, whether it is biometric based authentication, but authentication is one of the defensive mechanisms where you can prevent unauthorized or users from accessing your network resources. Then obviously, in order to prevent from sniffing kind of attacks, you can always use encryption. And in fact, encryption is the only solution to prevent sniffing attacks. Then, in order to prevent modification by the attackers, we use integrity checkers or hashing algorithms like SHA, like MD5, MD4, SHA-256. CRC32 is also there, but it's a non-cryptographic checksum. But the idea is that you want to prevent modification of your data. You can also use access restrictions like password protected VPNs can also be used to restrict the access. Then we have firewalls that can filter the incoming and outgoing traffic. You can detect DOS attacks, for instance, and several other types of attacks, or that the traffic can be filtered based on IP addresses, based on the contents, based on the data that is being carried in the packets. And these are, like I said, these are not the only solutions. You have intrusion detection systems, you have endpoint security as well. So when we talk about security, we generally have the principle, we call it defense in depth. So with this, we have almost completed the chapter. Let me just give you a quick review of the protocol layers and service models. So networks are basically complex. They have hosts, they have routers, they have switches, physical media, applications, we have protocols. So the question is that how do we organize this whole, process of communication in the networks? Like sending a message from one host to another, how can we organize and understand this whole structures? So in order to understand, we are going to use an example of air travel, for instance. So the airplane usually, carries people and luggage from one end to another end. And there are certain steps that we need to follow. So from the, origin point of view, we have to purchase a ticket, then we have to, get our baggage checked. We have to go to the gates, and then we have to go to the, plane, board on the plane. The plane will go to the runway and take off, and then an airplane will follow a specific route to reach its destination. And on the destination side, again, same process will have follow in the reverse direction. So it will land and then We'll go to the gates, we will claim our baggage, and we will basically reach our final destination. So this is just an analogy to understand how the communication happens in the networks. So let me quickly take you to the um, internet protocol stack. So we have application layer, we have transport layer, we have network layer, we have link layer, and then we have physical layer. So on the application level, we have different types of applications, HTTP, SMTP, we have DNS, IMAP, and there are several other types of applications which are there, which use certain protocols. So from the application layer, the data is passed on to the transport layer. Just like we took the example of airplane that first you need to purchase the ticket and then you need to, uh, you know, um, you need to book your luggage and then you need to go to the gate. So we are following the similar kind of procedure that an application has data to send. So let's just say that we are talking about a web application and we are making an HTTP request. So that request will be passed on to the transport layer that the transport layer is going to process the data and append some headers to it. So there are two protocols that exist on the transport layer. We will study more about them in chapter number 3, TCP and the UDP. And then from transport layer, this packet will be forwarded to the network layer. The network layer will again put some information about how the packet is going to be routed, and it puts the source address, the destination address, and the routing protocols. They also work on the network layer. So a route will also be decided, and then we will have the data link layer, which basically creates the frames, appends the MAC addresses, and there are certain protocols which also deal with accessing the media. So media access protocols are also there on the link layer, and from link layer, the bits will be transmitted onto the wire. On the receiver side, the packet will be received in this, and will have to go through the same layers. So it will go from physical to the link layer. The link layer will remove the header and pass it on to the network layer. The network layer will remove the header and pass it on to the transport layer. The transport layer will remove the TCP header and finally send the data to the application layer. So with this, I have completed this chapter. In the next video, I'm going to um, do some problems related to chapter number 1. So stay tuned and subscribe to the channel. Thank you for watching.